Welcome all for this topic on the post method of analysis, right? So, and post method and displacement method of analysis. Basically, we will be dealing with uh, statically indeterminate structure, right? So, things we cannot solve using equilibrium equations, right? And what is this force method? So, the simplest thing is force method analysis, it should satisfy the compatibility equation. What is compatibility? That means shape of the structure, right? Shape of the original structure, right? So they identify the redundant forces and they remove the redundancy by making it determinate, right? So once the redundant forces are solved, then we solve this entire system, right? So from the displacement method of analysis, what we are doing is we satisfy the equilibrium conditions, as we discussed before, right? So there we solve for unknown displacement, considering the equilibrium, right? Here in the force method, we satisfy the shape of the structure, that means the compatibility, and solve for redundant force. Here we solve for redundant displacement, right? And once the unknown displacements are known, we can solve for the unknown forces, right? So let me go take you back to the force method of analysis, right? So first thing is, so we need to determine what is statical indeterminacy and kinematic indeterminacy, right? So consider this, right? So yes. So let me refresh you on statical indeterminacy and kinematic indeterminacy, right? So indeterminate means you cannot solve it, right? You can't get an answer, a solution, right? So statical indeterminate means when your structure has more unknowns than the number of equations you have, right? So if it is you are in 3D, right? You have three number of equations where you can solve for forces in the x direction and forces in y direction and moment about dz, right? The third axis is the axis coming out of this plane or axis going into this plane, right? So we have this, right? If it is fixed support, it restrained each of these movements. So that means it will have a reaction in this direction, can have a reaction in this direction, and it can resist moment in this direction, right? So if it is a pin support, it does not restrain moments, but it will restrain these forces, right? Here it's a roller. So roller does not restrict this fx translation or any moment. So it will only restrain the movement in y direction. So it will then have a reaction like this. So altogether, this has, right? How much? 1, 2, 3, 1, 2, 3, 4, 5, and 6. 6 unknowns, right? 6 unknowns, and you have three equations. So your statical indeterminacy becomes 6 minus 3 equals to, right? So you need additional three equations to solve this structure, right? So if you consider this one, it is here. So there should be some kind of loading, right? Let's say it's like this. Okay, the loading applied, right? If your vertical is loading and no horizontal loads acting, so probably you don't have any reactions like this, right? Horizontal reactions are not coming to play, and you can't use that equilibrium equation as well, right? So remove that and the equation as well. So if you consider the kinematic, see, right? You consider this, right? So what is the actual meaning of kinematic indeterminacy? That means unknown displacements at each joint, number of unknown displacement at each joint. So you know, if it is not allowed to rotate, theta here is 0. If it is not allowed to translate in x and y direction, your deflection or the translation are 0. So here the three deflections, okay. So what are the unknown displacements? Right here, all the three displacements which can occur are 0. So those are known, right? Those are 0, right? But here you can see cannot move in this way and as well as this way, but it can rotate, right? And okay, but please theta, this is also theta. So there you have one unknown displacement, right? So here you have that theta because it cannot restrain any rotation, right? As here, but in the meantime, it can allow these translations, let's say delta. So from these three displacement which can occur, it can restrain downward translations, right? Here it will restrain downward and positive x directions as well. So it will only here no translations and no rotations. Here two gone, one is remaining. Here one gone, two remaining, right? So probably we have two unknown displacements, one unknown displacement, and here kinematic indeterminacy is 3. So let me call this axially rigid, right? So if it is axially rigid, this deformation in the x direction are negligible, right? So it is stiff, right? You know, if equals kx, so your k is increasing for the same x is reducing. So if k is infinitely large, your x is very small for the same force. So that means this can approximate to 0 and it becomes a known, not an unknown, a known displacement. So that brings you to if axially rigid, right? So we will move up with a simple example, right? So usually if statical indeterminacy is lower than kinematic indeterminacy, force method is preferred, and vice versa. If kinematic indeterminacy is low, you can use displacement method, right? So we will get back to a simple example. So you can see this, it's a fixed support and with two rollers, right? So there you have one reaction. So it does not have any horizontal loading. So probably I don't have any reaction for horizontal, right? So it will only have a moment and here vertical reaction and the vertical reaction. So together you have four unknowns. But how many equations you have? You have only two, right? Because you remove horizontal force from the system, and you can't use the horizontal equilibrium equation as well. So your three equations now become two. If you take horizontal equation, you are unknowns 5, and you have horizontal equations as well. So in any case, your statical indeterminacy is same, right? It is 2. So that means there are two redundants, right? Due to that, you can't solve this system. So the problem is how we are going to reduce. So there are many ways you can remove this, right? You remove two redundants, either BB, FA, or BA, BB, or BBBC, but be careful when you remove the remaining structure to be stable. Okay, so let's say you remove uh, something like this. You remove MA and BB. Then it becomes, so if you remove MA, it can't restrain further moments, right? So it becomes a simply supported, right? So if you remove B, there's no support here, it's also simply supported, right? Is that right? So this is something stable, right? And determinate. Now you can solve this, but it's not the actual structure, right? So we have to do some modification. Let's see what, right? So this, so I'll take the redundants as BB and MA. So we have to determine sign convention, right? So our sign convention is clockwise positive and upward forces and displacements positive. So if you consider clockwise moments, clockwise rotations are also positive rotations and moment, forces and displacements. So usually we use forces for both moment and forces, and we use displacement for both displacement and the rotation, right? It's a common term, but make just please be aware of the difference, right? The rotation, so rotation is corresponds to a bending moment, and the linear displacement is corresponds linear displacement corresponds to a linear force, right? So yes, we can go ahead and our redundants. Okay, redundant are MA and B, right? So I'm going to remove this. So once I remove that, my structure will be like this. Structure is like this now. So it is no longer the original structure, right? Is 2L. I remove the structure, right? So this will be, I call it BAS. I call this primary structure, right? I remove the redundance and make it determinate. We can solve this, right? We can solve for forces because the statical indeterminacy was 2. So that means two additional equations are there. So what we did is we remove two forces. Then our equations are enough, right? So BCS, right? So you can determine this. So this is a determinate beam. And what you should do is then, so we remove a force, right? So let's call this, so I need to have a redundant coordinate system. So I'll call this first redundant, the BB. Okay, first redundant. This is the second redundant. And make no mistake about that, the sign convention is still valid. So this is clockwise positive for rotation and bending moments, and upward positive, right? So I'll call this, it's originally in the up clockwise direction, so it is positive. So if I solve it and ended up with a negative answer, so that means it's in the anti-clockwise direction. So it doesn't matter because we need not to know the exact direction at the beginning if it is an unknown, right? So what we are going to do is superimposing these events, right? So one thing is we now have loading on the structure, so we need not to consider the loading in any of these two structures, right? So what I'm going to do is, if I add these three structures, I need to maintain the shape of the original structures, right? So you just need to consider where in which you remove the redundant. So 1 and 2, and you have to maintain the shape, right? So you remove let me talk about the first redundant. So you remove R. So it's going to deflect like this. And you remove MA as well, it is going to rotate as well, right? So this is due to, let's call this T1. Okay, let's call this T2, right? So you remove the redundance and the shape changes, right? So now this is the shape at B, and this is the shape at the rotation at, because the moments are corresponding to the rotation, right? You remove the restraint fixed clamp, so it can rotate. So it will rotate T2, right? So now it is not the original structure. So what you are going to do is you remove the force and you apply one at a time, right? You remove the force first and then the moment, and you are going to apply a unit force here. Why unit force? Because if you apply a unit, you can easily determine the things and you can multiply it by the original value, right? It's very easy. If your force is 1 kilonewton, so you can calculate easily the reactions and you can multiply it by that the original force, and there will be the original reaction. So you apply one unit load, right? Unit load. So make unit redundant. So what are the actions we need? So if you remove these, right, the actions remaining is BA and BC. So I'll call this the first action, and this is the second action, right? So this is the first redundant, right? This is the first redundant, and this is the second redundant, right? So I'm going to apply a unit force, right? If you apply a unit force, probably he will deflect like this. So now consider the shape at B. It will have some formation, right? Like this. It will have some rotation like this. So since you apply B, it will not apply a deflection to E, as well as it will apply a rotation to A as well, right? Since due to this unit force at B, you need to consider both. Due to this force, both redundant coordinate 1 and 2 gets affected, right? And apply then a unit moment, because you remove the unit bending moment there, and you have to apply a unit moment, right? So I will apply it in the clockwise direction, right? So because this is my clockwise direction, right? If you do like that, so you have something like this, and there will be some tension and there will be some displacement due to this unit bending moment, right? Due to this unit bending moment. So what we actually be doing? So you know F equals kx, right? So we are applying a unit force. So that means 1 over k equals x. So we are taking the displacement, right? So that displacement is 1 over k. So k is stiffness. So 1 over k means flexibility, right? Right? 1 over k means flexibility. So that's why we use the term F, right? So displacement per unit force is the flexibility coefficient. This displacement is a flexibility, how much it deflects per a unit force, right? So we use this notation as, let's call this F1, 1. So this notation system means the deflection at first redundant coordinate due to the force, the unit redundant at first coordinate, right? So this is F21. That means the displacement at second redundant coordinate due to the force at first redundant coordinate. So in such case, this should be F22. Displacement at second redundant coordinate due to the force at second redundant coordinate. And this is F12, right? So that is displacement at the first redundant coordinate due to the unit redundant at second redundant coordinate, right? So once you find this, you can match the shape, right? So it is still for a unit force, right? So for a unit force, you will have some reactions as well. So this will have, we call it a action unit. So this is our first action coordinate, action unit 1, due to the load at first redundant coordinate. Okay. So this is So these coordinate systems are different. Okay, so this is 1 and 2 for redundant, and this is 1 and 2 for actions. Okay, but this is the second action due to the load at first redundant. Okay, so this is action unit 1 due to the load at second redundant body. This is action to action unit 2. It's action unit 2, second action coordinate due to the unit force at second redundant coordinate, right? So I'll mark this everything upward as the positive direction according to my sign convention, right? So what should happen, right? So it is still not the actual. So if you apply unit force and calculate things, so what will it be for your actual force VB? So your actual force is VB. Then you just need to multiply it by the original VB value, right? If you multiply it by VB, so this will be your actual displacement for a VB force, right? Just need to multiply it by VB. You remove the VB and apply a unit force and get the output, and you multiply the output by that value. Because people have derived this appendix for this displacement for a unit force, because they can't derive it for every force. So it's easy if we use unit force, and we can multiply it by the value V1, right? So we apply a unit moment, but the actual moment is MA. So we need to multiply everything by MA, right? Like everything by MA, right? So okay, now we need the shape of the structure. First, we check compatibility, right? So if we check compatibility at B, the shape, right? At B, you don't have any settlement. So that means probably your displacement, the shape of the profile is zero, right? It does not reflect because it is well supported. But if you have a support settlement, let's say delta, that's your deflection, right? In the original structure. So that means in the force method, we can compensate the support settlements as well, right? So deflection here, the shape is zero. And here the rotation, the shape at the second redundant coordinate, because it is support, it does not allow any rotations, right? So that means theta is zero, right? So that is the original structure. Let's now call it from the primary structure. So at the primary structure, we have a displacement at E. It is D1. Still, I did not check the sign. Probably it should be negative, but you can refer the appendix and take it. Okay. So here it is D2 at second coordinate. Yeah, that's a rotation. Right. So plus, and here you have something, right? So here at B, the deflection is F11 into VB. Here the deflection at B is F12 into MA. right? At C, you have F21 into VB. Plus, these are all simple terms, right? Simple F, flexibility. F22 into MA. That is the shape of each structure at B and C, right? So that gives you, right? If you add these three structures, so you originally, so wait a minute, if you add these three displacements, it should be equal to the original displacement of the structure. Originally you had 0, then you remove that, then it had d1, then you apply that unit force, okay, check the reaction, right, and check the displacement, and you multiply it by the original value. Then you have some component, and not only that, you have another redundant. Because of that also you have a displacement at B. So we consider one at a time, one redundant at a time. So there will be two components, right? Because this EB is not only the contribution to this displacement, MA also can. That's why you get a component from here as well, right? And then you can simplify this. And yes, as you can determine the actions as well, right? The original actions at B and C. B and C, you have A, sorry, not B and C, the action coordinates. Those are not the redundant coordinates. BA and BC equals to, this is the original structure. So in the primary structure, you have BAS and BCS. And here you have AU11 into EB and AU121 into EB. One B and AU21. Here you have at A, AU12 into MA. Here you have AU22, MA, right? So from here, you can simplify this. So you can take this BB and MA out and form a matrix. From there, I consider, so that was 0 from the previous slide, okay? This is not. So from the previous slide, okay? So you had 0. So this is your D matrix, D1 and D2. And you can take those out. F11, F12, 1, and F2. Yes, BB and B M A. Right, so you have So you can simplify this. So it is 0. So you can write this as 0 matrix. So this is, if you have a settlement, you can simply give that settlement to this element, right? If there's a B settlement at B and C, you can have some value for this element and this element, right? For now, it is 0. This is the D matrix, the displacements, the primary structure. This is, you write the flexibility matrix. So we use square brackets. Why? That flexibility coefficient does not depend on your external loading. This is the force matrix, right? So this is the classical force method equation, right? So yes, you know these things, right? So you can determine this, you can determine this, you can determine this, and you solve for this. Can you see that if you consider this one, you can write something like this. This is the action matrix. The things remain in. But once you find this, you can just again just take the equilibrium and find these actions as well, right? So there are several ways to do, but you can solve this is still using the matrix method, right? So we call this AS, sorry, action all these actions in the primary structure. And if you take this, you can tell this AU matrix. There will be 4 coefficients. Again, you use square brackets that does not depend on the external loading, right? And here, because those is contain something applied for a unit force, that is always a constant for a unit force that does not change, right? So this is PV and MA. So what is this again? Again, this is the force matrix. So once you solve this, you can plug it back here and you can determine this, you can determine this. You solve for this. Okay. So I'll consider this is my first step. This is the second step. This is the third step. Okay. So we are going to do this. For the first step, you had removed PP and MA, right? So it's going to be like this, right? So you need to determine this D1 and this rotation D2. And at the same time, the actions as well. PAS and BCS, right? So you have some loading as well. This is 2L. Please consider that it's 2L. And yes, this is D1. So we need to find at each step, we need to find the displacement and the actions, right? The force method, forces, and the action, right? So equilibrium forces and the action. So here you need to find displacement at each location and the corresponding action, right? Which is need to be found, right? So here and E1. So we need to refer the appendix. So it's like this, right? So here they consider the positive direction, the displacement, and downward clockwise rotation for their sign convention. So your sign convention is positive direction, displacement is not the downward direction, it is upward direction. So when you take values from this appendix, just take the value and consider the direction from according to your sign. Okay, so this is the structure you need, right? So you need at the middle F1 and F4, right? F4. So F1 is pretty straightforward, this one. So you need to apply, this is 2L, right? Q is W and L is actually 2L. So your things getting 5WL squared. So that means 2 to the power 4, 2, 3, 8, 4. So once you plug this, you will end up with 5 over 24 because this L is actually 2L. So 2L to the power 4 means 32, so 16L4. That 16 is getting cancelled with this 384. So you'll be remaining 5WL4 over 24 EI. And the F4 is W L to the power 3. So L means 2L. So it is 8L cubed. So 8 is getting cancelled with this 24. And how about that? So that value is 8 over 24 means WL cubed over 3EI. Right? So your T1 was 5WL4 over 24 EI, right? And D2 was WL cube over 3EI. Because your L is actually 2L, okay? Appendix, you have single L, right? So how to determine the sign now? So it is actually in the downward direction, right? So that means this is negative according to your sign convention. Why? You took upward deflection and upward forces are positive. Here you took clockwise rotation and clockwise moments are positive, but this T2 is actually in the clockwise direction, right? Original position was this, now it has clockwise rotation, so this is positive, right? No problem with that. So this is simple symmetrical beam. So this can be evaluated by 2L into W divided by 2. So that means WL. This is also just WL, right? It's symmetric, right? So now so our first step is done, right? The primary structure is done and dusted. And we go back to the second. So here you don't have any loading. What you are doing is basically applying that unit force. See, so this was F1, and here it was F21, and this is AU action coordinate 1 due to the unit at redundant coordinate 1. So here the action of 2 due to the redundant unit load that redundant coordinate 1, right? So if it is F1, so we need to again consider the appendix, right? So go back and here. So that's the key. Here you apply a load and underneath that. So just take the mirror image, okay? Just think about mirror image. So appendix is downward force. we are giving an upward force, but it is a unit force, right? So our P is 1, right? P is 1, right? So B is the distance to the load from the left end. So now B is actually L, because our beam is 2L, right? The place where we want is actually as the middle, right? We apply the load at middle and we take the displacement and middle. So that means the X is also L, right? At the end, we can take F2 or F3 either, right? We take F2, right? Doesn't matter. If these are two, this is symmetric. This becomes then symmetric, right? So if it is P1 and we are going to use P6 for F1, okay? So doesn't matter if x less than or b or x greater than b, because at x equals L by 2, both of them are valid, but make sure this equation, I think it had some mistake, because the units of these two are not tallying. So please use this one. Even in the book, they have used this append, this equation, right? So now our x is L, b is L, b is 1, right? So this one, this L, this L is actually 2L, right? L is actually 2L, right? So write out these things when you are taking something from the appendix. Then you are not mistaken, right? So once you plug this, right, you will be ended up with 1, this is L, 2L minus L is again L over 6, this is 2L I, right, into this is 2L, L, that is 4L squared. This is L, this is L, so altogether 2L squared. So you ended up with this 2, right? Yes, it is 2. And here it is 4L squared, it is 2, where the 2 is, so this becomes L is getting cancelled, 2 is there, so probably L to the power 3 over 6 E, right? So you have this, right? This is F11, right? So we take the mirror image, so it is in the upward direction, so it is positive, right? So now we need F2, right? So what is F2 here? Okay. If P is L by 2 also, whatever, you can take F2 as this. So actually our L is 2L, right? So 2L squared means 4L squared. So that 4 is getting cancelled with this 6, right? So that means your F1 comes L squared. So P is 1, it's a unit force for E, and that is, yes, we'll take this and go to the appendix. The F F11 is L cubed over 6 and your F21 minus L squared over 4EI. Why minus? We took magnitude from the appendix, but it is in the anti-clockwise direction, which against our sign convention. That's why we use minus, right? So if we carefully continue this, our F21 is exactly equal to F12. There's a theory behind that, right? So I'm not going to focus on that theory. So if your F21 is not same as F12, that means probably what you are doing is wrong, right? So that should be exactly equal to F12, right? So if you apply 1, so it is again symmetric. So AU12 and AU11 will be 0.5 and negative, right? So negative and 0.5 because you apply 1. So that means the reaction should be in the downward direction, right? So that is straightforward. So our second step is also done, and we are going to third step. So we apply a unit rotation. Right. So this is F22 displacement. Actually, it is a displacement, but it is for a unit force. So that's why we use flexibility. F1, 2, right? So if you apply a moment like this, not only this place will rotate, this place also we have a deflection, right? So we need to consider that as well. So let me get back to the appendix and the appendix. So if you apply a moment like this, you should consider F11 and F4, right? So F1 is at the corner and F4 is at the middle. So F1 is, so now your moment is 1 unit moment, L is 2L, so it is straightforward 2L over 3EI. Problem. And here you have M is 1, L is 2L, so that is L squared over 4EI. Because 2L squared is cancelled with 16, right? That becomes L squared over 4, right? This is exactly the magnitude as the F21, right? So this is F12. Can you see? So we will determine the sign as well. This is 2L over 3pi, right? So F12 was L squared over 4EI, and now it is in downward direction. So we consider upward positive. So that is exactly negative as F21. So that means what we are doing is totally correct, right? Fundamentally correct. So F22, right? So F22 is how much? 2L over 3EI. And you can determine these reactions as well. It's AU12 is AU22, right? So you can consider the equilibrium. So I'll call this lambda because I'm too lazy to write this again. And mu. Lambda and mu. So that means if I take the horizontal equilibrium, lambda plus mu equals to 0. Because there is no any external force, only this bending moment, right? So if I take moments above A, lambda is not coming, mu is coming. So clockwise direction, clockwise positive 1 moment is here, mu is not coming. and this is anti-clockwise. This is mu into 2L. So that means mu is 1 over 2L. This is 1 over 2L. But addition of these two is 0, so that means this is minus 1 over 2L. Right? In that case, so you consider the actions and the displacement. So this is okay now. So your third step is done, right? So this was done. We found D2, we found this, we found this, we found this, we found these things, right? We found these things and these things. We found this, we found this. To take the compatibility, we need to try multiply this by original force, right? At second step and third step. So we need to multiply these all things by dB, because that is the actual value at B. And we need to multiply these all things by MA. That was the actual moment at A. So when you do, you'll end up with this. So we can check now the equation, right? 0, 0. So you have 0, 0, right? And the force was D1 and D2, right? D1 and D2. What was D1 and D2? D1 and D2 was this one. 5WL squared over 24 EI, WL over 3 EI. So we are checking the compatibility, right? Okay. And over EI. Right? And then we have flexibility coefficients. Remember, it's L cube over 6 EI. This L cube, L to the power 3. So this was L squared over 4 EI. L squared. So this is 2L over PEI into force. So what is the force? PB and MA. Right. So we need to determine this. So we are taking this to left hand side. So that becomes, I can take WL cube over 24 EI out. Okay. So this becomes negative as well. So that if it is here, it is positive 5 and this is negative. Okay. So negative coefficient will be here, positive will be here. Okay. WL cube, you are taking out 5, 5L, right? WL cube over 24 EI. So this is WL cube. So that becomes 8 minus. And what I'm doing is I take L over 12 EI out, right? So this becomes the squared. This becomes L 2L squared. out. This becomes minus 3L, right? Minus 3L. This is also negative. F21, F21. Remember those are equal, right? So we are taking out 12. So this means 8. So this is square bracket. So this is the force matrix you need to find. So you need to multiply. This is the F. So I call it K and plug it back to the original. So it is 2L squared, okay, 3L, okay. It's also 3L, okay, and this is 8K. So to solve this, you need to multiply both by, this is the F matrix. You need to multiply both by the F inverse. So if you multiply this by F inverse, the game over, right? If you multiply this by, so then you have to multiply both by F inverse. So F inverse into F inverse brings you I, the unit matrix. Unit matrix into any matrix is the same matrix. So that means you can solve for F if you multiply F inverse by this matrix, right? So if you find, so this is the determinant. Determinant is main diagonal multiplication, subtract its sub diagonal multiplication. It is 16L squared K squared minus 9L squared K squared. So that becomes 7K squared L squared. So you need to divide each by 7K squared L squared. So once you find F inverse, it will be 12 pi 7L cubed to 8 to L. Yes, this L. Yes, it is L squared. That is the L. Right? Okay. So just check this. If you have a mark, if you have a 4x4 matrix, what you are going to do is to interchange this coefficient and you multiply the subdiagonal by -1 and you divide it by the determinant. That is your inverse. Okay. Let's check this. So when you multiply this by this matrix, okay, you can multiply these values together, right? So you will be remaining F matrix as A, E, sorry, A, you will ended up with 8 L 7 up to S 14 into minus. Check this value. Okay. You just need to multiply those two matrices, right? So you can see it is minus sign, right? So that means you consider clockwise, but it is actually anti-clockwise direction, MA, right? MA is originally anti-clockwise moment. So once you know this, you can go ahead and plug for this. So you know the actions in the primary structure WL and WL and the action unit. So it is 0.5 here. You know this WL. Now you need to multiply this by BB, and that was taken by the matrix. So AU1 and AU2. So from the second one is minus 0.5 and minus 0.5, right? And here it was minus 1 over 2L, AU1. Here it was plus 1 over 2L into F, this is, right? So we shall go ahead and multiply this one. WL so we can go here, separate WL out from that first matrix. So 5 minus 1 over 2L into, so I can take WL over 14, right? WL over 14 I can take. WL over 14, if I take this, it should be 16. Be 16. It should be minus N, right? Minus N. So I can peacefully multiply this. So I can take this in the front. So matrix multiplication. WL over 14. So I will make this as WL over 14. If it is WL over 14, the coefficient it should be 14 and 14. So when you multiply 1 over 14 into 14, it's 1. 1 over 14 into 14, 1, right? So minus 0.5 into 60. So that is 8, right? This into this into this. So minus minus plus. So that is plus L getting cancelled, plus half, right? Minus 0.5 into 16, so it is minus 8. Minus 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 0.5. So it is minus 7.5, right? And this is how much? So I can take all this WL over. So that is 14 minus 8 plus 0.5, 14 minus 8 minus 0.5. So what are the answers we are getting? 8 minus 8 minus 5. So that means 14, 11 over 2. the other answer is 13 over 2. So this should be 13 over 2. This is 11 over 2. So if you plug it back, this WL 13 WL to 28, and this is 11 WL to 28. That brings you VAN. So these are original positive, so that means need not worry, those are according to our sign convention, those are positive. So we consider the compatibility and solve for the F. Once you find F, right? Find F, go ahead and plug it back. So if you find F, there's no need to find like these actions, right? If you know these forces, you can just take the equilibrium and get these forces because you already solved EA and MA. You can just take a pending moment or something and find BA and BC. It's not going to take that much time compared to this, but this is the standard procedure, right? So thank you very much.